Okay, so I'm going to present our work STranGAN, that is Adversarially-Learnt Spatial Transformer for Scalable Human Activity Recognition. Oh, give me a second, please. It's not properly full screen. Yeah, it's better, right? I'm from the same lab as my previous presenter, so yeah, 2 papers in this conference from our lab, so we are very happy about that. So okay, so let's get down to the overview of today's presentation. So we start with the motivation for wearable sensor-based human activity recognition, and then we actually dive down to some of the challenges with building such models, such as heterogeneities in the data distributions. And then we touch bases on some of the related works on ways to handle the heterogeneities. And then we talk about the methodology that we have developed, that is adversarially-learnt spatial transformation. We then dive down into the experimental setups, that is data sets, preprocessing, and model building. And then we evaluate and discuss our results on cross-body position and cross-person transfer. We talk about the interpretability and conclude our presentation with a small discussion. So, what's the motivation for doing wearable sensor-based human activity recognition? So as you all know, that in the last few years, the proliferation of the low-cost wearable sensors and IoT devices has actually created a plethora of opportunities in healthcare, sports analytics, fitness monitoring, entertainment, and skill acquisition training. And one of the reasons that people actually love working or classifying human activities with IMU sensors is that the accelerometers, gyroscope of the magnetometer that are in these our wearable devices, they are actually very flexible. I mean, they have inbuilt some qualities, like they are a little bit privacy preserving. Nobody's actually taking your pictures or videos, and also like you can wear a watch and you can move about, and yeah, it's pretty flexible. At the same time, that actually creates a lot of challenges, mainly the heterogeneities in the data distribution from personal and heterogeneous streams. Like you can have variations in age, sex, dexterity. If you are talking about an activity that has a learning curve, then you also might have to take that into account. So let's talk about some of the other challenges. So apart from the cross-person heterogeneity that I already talked about, there can be cross-device or cross-position heterogeneity. Imagine a situation that you already have probably a trained classifier that was trained on your data collected over your phone for the last few years. Now you want to, you have gotten a new, say, wristwatch, and you want to leave your phone behind. You want to actually be able to have the same accuracy as you would have before, but then you have actually introduced 2 heterogeneities. One is that the sensors in your wearable, like watch or anything that you are, so that might be a little bit different. It might have its internal, the signal processing techniques might be a little bit different, the sensitivity might be different, so that introduces a sensor bias. And also you have also introduced the cross-position heterogeneity, because now you're wearing the wristwatch on your hand, your phone probably kept in your back pocket. So 2 heterogeneous at the same time. So this can make the models, that previously trained models, very difficult to work with the new data. So we asked ourselves this question before starting this project and see that how to actually handle this kind of things. The obvious thing would be to actually collect more data and label them, but that's not a feasible thing. So we asked 4 questions, like how do we scale activity recognition models across heterogeneities with limited label samples? Can a model learn a good feature representation from more readily available unlabeled samples? So we don't need to label the data samples, but can we actually still learn some feature representations from unlabeled data? That is easily, we can easily get them. And also, do we need to retrain the classifier when we learn these representations from the unlabeled data? Can we interpret these learned representations to find the reasons behind the heterogeneity? So these are some of the questions, and we'll see if we can answer some of these as we go by. So what are the common ways to handle this kind of heterogeneities? The most common way is like, people use domain adaptation is very popular with feature alignment, where previously people used to require a little bit of label data in the target domain, that is the news data, the heterogeneous data that you're working with. The original data that you already have the classifier trained on, that is normally referred as the source domain. So I will use this terminology from now on. Nowadays, people have moved down to fully unsupervised domain adaptation, but in most cases, people rely on still collecting synchronized data, unlabeled data between the source and the target domain. So that is one roadblock. There are also adversarial approaches that you can use to learn a domain invariant feature representation, so your classifier should always work. And actually, sometimes the most simple way is the best, is the data augmentation, right? I mean, there has been some works recently where you just randomly rotate or scale or apply shear transformations on the input data, and you hope that your classifier will perform better. And it turns out that it actually works well. We actually, in one of our previous works, did actually just that. But then another question arises. How do you know which transformation will work? I mean, often the case that we will just apply a set of transformations in a very narrow band, and then we'll try to see, oh, this works. That is like trial and error. So we said to ourselves that what if instead of doing that, what if we could learn that thing in a machine learning, with a machine learning paradigm? So our approach that we have actually suggested is learn an optimal set of raw data transformation via an adversarial learning without any label samples for either of the domains. So let's dive down into the methodology. So again, I'm trained. So the classifier would not have any trouble actually classifying those samples. So that was the idea. Now the question becomes, how do we actually model the parameters of these transformations? It turns out it's actually pretty simple. So any combination of rotation, scaling, shear, or translation can be actually expressed by a 12-parameter matrix. Given an input acceleration vector u and an affine transform vector v, so our problem statement becomes learn the transformation parameters a theta so that this equation fits. And I have given two examples where if you want to scale by a given axis by a very certain amount, or you want to translate the data by a certain amount, or you want to rotate the data around a very certain axis, you can actually do that. So it is possible to actually handcraft these transformations, and that's what people do when they are doing data augmentations. But we just said, okay, instead of doing that, just learn all the values of this matrix, these 12 parameters, and we should be able to express any complex transformation that we want to have on the data. So how do we actually, now the question again devolves to, how do we actually learn these 12 parameters, right? So, and here's the thing that we came up with. The idea is to scrutinize the unlabeled samples, that is BT or the target batch, with the localization network, that is L, regress the 4x3 parameters for the transformations, get the transformation samples by multiplying that target data with those set of parameters, and then get a discriminator, because your expectation is to have the distribution of the data that you have just transformed to have the very similar distribution of the source samples. So have a discriminator to differentiate between them. And as you have you would guess this is actually a generative adversarial network. And during inference, if we can train this network, during inference, all we need to do is pass the data through the transformer network and then basically use our classifier. So we never touch the classifier that was previously trained. So that is something different from other frameworks. Now, as you would assume that the generator loss and discriminator loss are very similar to the vanilla GAN that was proposed in 2014. But here, because we are doing a set of transformations, the T might learn a very small set of transformations to fool the discriminator, and it doesn't have any label information, so it might cross the label boundaries. It might just say, oh, I can just put it in that place, and it just memorizes that, and every sample will be mapped there, and the classifier will actually fail. So our solution to handle that is to apply transformations only on heterogeneous and target samples, and leave the original samples alone. And that can be easily done by actually having a reconstruction loss, where if the network sees any source samples or any sample that has a distribution similar to source samples, it would just do an identity transformation. So that actually regularizes this part of the loss quite a way. So that actually concludes our methodology. So let's move on to the experimental setup. So we used 4 data sets. These are very much used in the literature, HHAR, opportunity, and PAMUP. The PAMUP actually has the highest variance in terms of subjects and labels, whereas opportunity actually has the highest variance in terms of position heterogeneity. Also, HHAR and PAMUP2 actually are more balanced than the opportunity data set. And this is the internal structure of how we actually the internal structure of the spatial transformer network. As you can see, give me a second, please. As you can see, the localization network itself actually consists of a convolutional subblock that actually has 12 parameters to regress, that is reshaped to 4×3, and then that is multiplied. So if you are familiar with attention mechanisms, that localization network can be interpreted as a key or query block, whereas the input is actually the values. And the discriminator is a normal, convolutional classifier. And these are the, model and evaluation details. One of the most challenging thing in this project was to stabilize the GAN training, because GANs are notoriously difficult to train sometimes. So we had to try a lot of things, and over time we figured out this setup actually performs pretty well. And also we prefer a shorter window with much more overlapping samples, because that actually helps to ensure the successive dissimilar augmentation is smoothed out to present a non-uniform transformation across track. So let's take a look at the results. Before going there, just a recap of some of the baseline that we have used. These are all state-of-the-art and chosen specifically to be the best among their within their methodology. Like STL is a subspace manifold alignment-based method, and others are also best in their category. But as you can see, each one of them suffers from at least one demerits, like they either require paired samples, or they are actually modifying the classifier, or they are not interpretable at all, whereas we actually check all the boxes. And in cross-body position, we actually realize that we actually get up to 5% improvement over the GDA with synchronized samples. Without synchronization, which we don't require, we actually get much higher, up to 7%, I presume. Similar story in opportunity data set. And, but in the cross-person transfer, we actually don't get that high. It's still 1.5 after successive runs. So we can say we are still competitive, but it's not, we had actually higher expectations, but we are not getting that high, and we think that we probably have a hypothesis on why it doesn't work. So what we actually think is that transformation needs to be affine. That actually introduces a restriction on how STranGAN is able to perform in different scenarios. And it leads us to speculate that position-specific heterogeneities are more affine in nature. And also on the interpretability. So if we take the probability density plot of the parameters that we have regressed, we can plot those out, and also we can take an before and after comparison of superimposed comparison between the target and source samples. You would see that there is much more overlap after applying the transformation, and some of these actually can be traced back to the transformation matrix. For example, you can see that there is a positive, so this column actually means how much translation was applied. So there is a negative translation, there is a little bit positive, and you can see that the peaks are actually abiding by that rule. And also this can also be traced to the diagonal of the matrix where the scale parameters are. But it is actually a little bit difficult to interpret this way, because this is a composite matrix. So this actually has all sorts of transformation, not just scaling or translation. It might be something complicated. The reason is there are other ways to do about it, but that would require us to do like reinforcement learning, and that would probably complicate our methodology a little bit more. So we think that STranGAN provides a nice trade-off between complexity, inference speed, and interpretability. And here's a graph of why we need to have that reconstruction loss. And if we turn it off by setting it to 0, you would see that the model actually fails to converge. And so this is something we found that without this thing, a vanilla GAN framework will not work. There are some of the these are some of the feature works that we want to pursue later on. Since our model doesn't require the classifier update, so it inherently has some privacy preserving aspects. So we would like to see whether it actually is complementary to federated learning or other privacy preserving models. And we would also like to investigate on more complex activities and gestures, more heterogeneities. We actually didn't get a time to do a lot of experiments on sensor heterogeneity, so that's something we want to investigate. And lastly, our whole idea is actually dependent on that there should be the label distribution between the source and target domain. Even if we don't have the labeled, we don't use the labeled data, but we assume that the overall label distribution should probably be same, and that is what guides the whole network. If the label distribution is widely different, we expect our network to actually fail. One way to go about is to use a pseudo labeling or some other mechanisms to provide feedback to the classifier, but that would actually defeat the purpose of having a decoupled classifier. So I think that's more all about it. So in conclusion, we built a decoupled interpretable domain adaptation method to mitigate personal and positional heterogeneity without any fair samples and achieve state-of-the-art results. Thank you all for listening, and we also want to acknowledge the funding bodies. I can take questions now.
We have time for one question.
Thanks for your talk. Your work is very impressive. And you mentioned that you use a matrix to formulate the transformation from source domain to target domain. And the matrix is